What up, everyone? I'm going to be talking about the characteristics of hydrogen water in this presentation. I think this is a needed presentation because hydrogen water has kind of exploded in the last year, and there's been a ton of new interest, but there's also been a ton of confusion, misconception, skepticism, all this kind of stuff. So, this won't cover everything about hydrogen rich water, like some of the medical benefits, but it will talk about the physical characteristics of hydrogen rich water. Because a lot of people at face value say hydrogen water, hydrogen's already in water, it's got to be a scam. So, I'm going to go ahead and show you in this video um, some of the science behind hydrogen rich water and how it works, what hydrogen rich water actually is. So, let's get into it. All right. So first and foremost, if you don't know who I am, and it's your first time to my YouTube channel, my name is Taiwan Hubbard. I am the CEO of H2 Hub, which is my hydrogen company. I'm also the creator of H2 Minutes, which is what you're watching. And so my YouTube channel, H2 Minutes, teaches around um, all all things hydrogen related for hydrogen therapy. And so this covers things like hydrogen rich water, hydrogen inhalation, the medical benefits, studies, different things like this. Even the related sciences around it. So I touch on things like water, and I touch on things like oxidative stress, different things that pertaining to biology and things like that. So my YouTube channel, H2 Minutes, is 100% crowdfunded or functions off donations because it is a free series on hydrogen therapy. And so we want to keep it that way. So that's how we function. And so if you do like this content, you like what I put out in this video, if you want to donate, you can always go down to the description and look at how you can do so by either being a member or going to Patreon or just a one-time donation. We appreciate it, whatever you give. So, but other than that, yeah. So that's Issue Minutes. Also, as I already mentioned, I'm the owner of H2 Hub. H2 Hub is my hydrogen company. In a nutshell, H2 Hub is the premier spot to go shop for tested and approved hydrogen products. So my company evaluates hydrogen products against basically in-house performance standards that are based on scientific research that correlates with other standards that are actually within this industry that have been set forth by authorities or industry leaders in this space, scientists. And we actually test these products against these standards to see which ones are up to snuff and which ones are not. And so if you see a product on my recommendation list or approval list, you know that we've tested it. And we've actually examined over 100 products on the market. I've been doing this for a long time. And we get to do consulting and things like that at Issue Hub to kind of help other companies know how to talk about hydrogen, how to go about being accurate when it comes to teaching about molecular hydrogen. And we also help consumers by finding products that are safe to use, that provide therapeutic levels of hydrogen, and actually have some level of build quality. So that's what I do every day at H2 Hub. So that's who I am. You can go check out my website, h2hub.com. That's with two B's, h2hub.com. That's with two B's. It follows by like my name, Taiwan Hubbard. So, alrighty, let's get it going. My presentation is called Hydrogen Water Characteristics Intro. It is an in-depth dive into the physical characteristics of H2 water. Let's go ahead and talk about this. Before we get into hydrogen, we have to talk about just gases and water, atmospheric gases and water. What most people don't realize is that atmospheric gases, the air we exist in, naturally dissolves into water, and we drink it every day. And so the concept of drinking water with a dissolved gas is not foreign to us. We actually drink, you know, carbonated beverages all the time. Carbon dioxide is a gas. Gives the water its physical characteristics. So the idea of having a different gas in water that can benefit us shouldn't be that far of a stretch. But sometimes it can be hard for us to grab these concepts off of our initial kind of presuppositions and beliefs. So anyway, we'll just go down through some of these points. All atmospheric gases dissolve into ordinary water, and our atmosphere is made up of a host of different gases, such as nitrogen, oxygen, argon, carbon dioxide, and hydrogen. which most people don't realize that you're breathing hydrogen right now. It's just very, 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 very low levels. Molecular hydrogen or hydrogen gas, sometimes referred to as dihydrogen, makes up about 0.00005% of the Earth's atmosphere by volume, roughly 1 millionth of the total. So 1 millionth of the percent of the total volume of air of our atmosphere around Earth is hydrogen. So this means that there are very low levels of H2 in our atmosphere. Now, there's a cool guy by the name of Henry who actually figured out the relationship between these gases, temperature, and pressure, and how they actually work to dissolve into water. And so my dog Henry, who made up a really cool law around gas, Henry's gas law, he kind of cracked the code on all this and kind of helped us be able to figure out this unique relationship. And so I'll read this point here because I think it kind of sums it up. The quantity of gas dissolved into water is directly correlated to the pressure of, let's say, 1 second. Why does that look like that? All right. Pressure, dissolved gas above, let's see here. Well, anyway, it's kind of got my slide block where I'm looking. Anyway, above the water at 100% concentration. So in other words, a way to like a way of thinking about this is that let's say you had a bag, and in that bag you had a glass of water, 16 ounces of water, 500 milliliters of water, and that bag was pressurized to, let's say, 20 psi. So, and that water had no, let's say, no other gases in it. It was degassed. If that was the case, if you put oxygen in that bag at 20 psi, oxygen is going to naturally dissolve into the water, proportionate to the pressure that is within that bag, that 20 psi, and you're going to get a particular concentration of oxygen in the water, a ppm concentration or milligram per liter concentration. And so this is how it works. There's a relationship between the gas, the pressure, and also the temperature. And so there's other things that affect it too, like the intrinsic property of a gas will affect how soluble it is in water. So, for example, the intrinsic property of carbon dioxide versus molecular hydrogen is going to affect which one's more soluble, which one's going to like to dissolve in the water more than the other. But regardless, all these gases are going to be subject to Henry's gas law. So all gases have a saturation point in which no more gas can be dissolved into the water. So there's going to be a ceiling. There's going to be, under normal conditions, there's going to be a maximum amount of gas that you're going to get into water, depending on the different gases. So for instance, for oxygen's saturation point, meaning the maximum amount you're going to get under a normal condition, basically SATP or normal atmospheric conditions, is going to be about 41.6 milligrams per liter or ppm. For those who understand right now, ppb, you've been looking at hydrogen water bottles, you want ppb, this would be 4100, basically. There's going to be a little bit above that, but basically 4100 ppb. So so that's basically what that's going to be. But the reality is that the water that you're already drinking, whether it's tap water, bottled water, whatever, is going to have about 8.7 milligrams per liter or ppm of dissolved oxygen in it, because our atmosphere is 21% oxygen. So what most people don't realize is that you're already kind of somewhat consuming oxygenated water. It's already in your water. So the concept of drinking hydrogen-rich water shouldn't be that far of a stretch either. But anyway, the math on this is pretty easy. Once you know the saturation point, you can times it by the percentage, and you'll get what is actually going to be the concentration for, at 21%. So you can see that as 8.71. So how much H2 is dissolved into tap water or conventional water? So this is interesting. So our ordinary tap water, bottled waters, rivers, streams, kind of things like this. Now there can be other things. I mean, there can be other factors that weighs into rivers and streams. But let's just say our ordinary tap water contains about 0.2 to 0.8 parts per trillion. So you already got hydrogen gas in your water. It's just really, really, really low levels. But this low level is due to the levels of H2 in our atmosphere. But like I said, these are crazy low levels. So that actually means that in 1 liter or 33.8 ounces of water will only contain about 8 millionth of a milligram of H2, 0.000000125 milligrams or 0.125 nanograms of molecular hydrogen. That's some really tiny levels. So this is why you don't derive any benefits from drinking tap water. Tap water, even though it contains very minuscule levels of molecular hydrogen in it. And it's because tap water has approximately 13 million times less hydrogen gas dissolved into it than hydrogen-rich water at saturation. So if you want to think about it this way, it has 13 million times less hydrogen gas dissolved into it than hydrogen water that has been deemed therapeutic by scientific research. So this is why we don't derive benefits from our tap water pertaining to hydrogen gas. So what is hydrogen saturation point in water? So hydrogen saturation point, if we were to take my example and we put another glass of water in there, and then we went ahead and put hydrogen gas in that bag and we pressurized it to about 15 psi, then what you're actually going to get is hydrogen saturation. Hydrogen is going to naturally dissolve into the water at that saturation point, or at that pressure, to produce this particular saturation point. So hydrogen saturation point is 1.57 milligrams per liter at SATP. SATP basically stands for standard ambient temperature and pressure. So think of basically about 77 degrees at sea level. That's basically what that means. And so this is actually quite low compared to other gases that basically dissolve into water. So for instance, you take your carbon dioxide. Carbon dioxide is over 900 times more soluble in water than hydrogen gas. So in other words, if hydrogen, let's say, for example, let's say carbon dioxide levels that are actually in, let's say, carbonated beverages, like a can of Pepsi or Coca-Cola. It's going to contain something like 6,000 ppm or milligrams per liter of carbon dioxide versus hydrogen over here. Its saturation point is at 1.57. So it seems really, really small. So it's like, wow, you're going to get anything from this and you're going to get kind of benefits. But anyway, this is kind of unanimously known as hydrogen saturation point. It's actually mentioned within scientific literature. And I already kind of explained SATP, but basically, like I said, it's about 14.7 pounds per square inch of pressure at about 77 degrees Fahrenheit. That's 25 degrees Celsius. This would be classified under normal conditions. So if that is the saturation point, can you get more? Well, yes, you can. More pressure equals more H2. So this is one of the issues you'll see out here. Sometimes I don't know if it's spoken of more. I don't know if it's spoken of as much nowadays by people, but it's probably still pitched out there that when you hear individuals say, "Oh, this hydrogen water bottle or this hydrogen device says it can make 3 milligrams per liter or ppm," and they say it's a scam because hydrogen saturation point water is 1.56 or 1.6 ppm or 1600 ppb. So therefore, that's a scam. You're not going to get those. You're not going to get those levels. Well, it could be a scam because the product just doesn't make those levels. But it does not mean that actual concentration, 3 milligrams per liter, is not achievable. If you can add more pressure, you can dissolve more gas, and it's just simply that simple. So, for instance, I have my little writing here that says that this implies that at 14.7 psi, the maximum achievable H2 concentration is 1.57 milligrams per liter ppm. However, if you increase the psi to 50, the maximum H2 concentration will be 5.35 milligrams per liter. That is 3.5 times H2 saturation point. So this is what's called super saturating the water with hydrogen gas. And this is another way of ensuring that you get higher levels of H2 in your body when you can pressurize hydrogen at a particular psi and dissolve hydrogen gas into the water. And so this is how you get higher concentrations. So here I state this. Therefore, it's important to understand that at 1.57 milligrams per liter ppm is the maximum achievable concentration when bubbling H2 gas into water in an open glass of water, but it's not the highest H2 concentration that can be achieved. So if, let's say, you had like a glass of water and you had a particular device that can produce hydrogen gas on demand, and you put that hydrogen gas, let's say via a tube or a diffusion stone, into a glass of water, and you just naturally bubbled it. Depending on your local elevation and the temperature of that water, you're basically only going to be able to maximally get 1.6 ppm. But if you were able to pressurize it and seal it off and still bubble it under, you're going to get more than that, because you're going to continue to increase what's called partial pressure, the PSI within that container, and then ultimately get to a higher concentration that can be dissolved into the water. So there's other reasons also why H2 concentration is going to be lower in water. It's not just the fact that it's just very small, low levels in our atmosphere. The other reason is due to hydrogen's kind of intrinsic properties. So this is going to kind of cover some of molecular hydrogen's properties. So first and foremost, hydrogen is a non-polar molecule, and it is neutral in its charge. So basically, non-polar basically just means that it basically equally shares its electrons. So it doesn't have any poles. It doesn't have any ends that pull electrons more to one side or the other. Like akin to like a really most popular polar molecule would be water, and it has this old little Mickey Mouse shape. And due to that kind of structure, or this 104-degree bond angle, you're going to have electrons get pulled in a certain way that you're going to have two poles. Well, hydrogen's not like that. Hydrogen is covalently bonded together, and it shares its electrons evenly, and so it's non-polar. And then it's also neutral in its charge. So hydrogen, molecular hydrogen, is made up of two protons and two electrons, and so therefore it has a neutral charge. So because of these two properties, hydrogen basically doesn't like to dissolve in water. Water likes polar molecules. And so polar molecules, you guys can go ahead and read this. I'll let you guys read this. I won't read it all, but I'll just explain some of it. Basically, polar molecules, things like salt or sugar, these substances will be called water-loving or hydrophilic. And so water loves these molecules because they can disassociate. And because of how how the water is structured, basically it can dissolve these molecules far easier. And there's other molecules that are like fats or lipids or things like this, like that doesn't like dissolving in water. And these would be non-polar molecules. And so they don't like dissolving in the water. This is where you get fat and water, or oil and water don't mix. And so this is basically, in a nutshell, what's happening with hydrogen. It doesn't like to dissolve in the water very well. And so this also aids to the fact of why it has a very low solubility or concentration or saturation point that is in water. However, this does not mean that hydrogen cannot be dissolved into water at a high enough concentration to be therapeutic for us. So this also goes into the properties of hydrogen, that hydrogen is the smallest and lightest molecule in the universe. So you can actually have a significant amount of molecules of hydrogen that's not reflected by like some kind of large weight. So in other words, you can have a lot of it at a low weight. And so this is stuff that's been talked about by other authorities in this space, such as like Molecular Hydrogen Institute talks about how you can have more molecules of hydrogen in a 1.6 milligram dose versus vitamin C at a 100 milligram dose. So it's kind of crazy, right? 1 milligram versus, or 1.6 milligram, sorry, 1.6 milligram dose versus a 100 milligram dose of vitamin C. So you can actually see that, where molar mass starts to come into play here, and the weight or intrinsic properties of a particular molecule. All right, so how long does hydrogen gas remain in water once it's dissolved? So when you actually dissolve hydrogen gas into water, um, and if it's sitting at normal room temperature, its half-life is about 2 hours, and it's going to totally equilibrate or dissipate fully in about 10 hours. And that's what this scientific quote talks about. However, what you need to understand is that its half-life is not some hardline rule. This 2 hours is not some hardline rule. There's many variables that can affect this, such as temperature, air pressure, nanobubble size, water volume, the container, the surface area of the water. All these things can affect hydrogen's half-life in water. And hydrogen is rather fragile when dissolved in the water anyway. So because of this, any agitation and things like that can accelerate its half-life, and how fast it actually dissipates out of water. So if you want to think about it this way, with this 2 hour mark, if you had hydrogen water at 1.6 ppm or saturation, and you left it out on your counter, you had like 500 milliliters of, let's say you have 500 milliliters or 16 ounces of hydrogen water at 1.6 ppm. You left it out on your counter, and you came back, and in 2 hours you want to drink it. Well, you could expect, if your house is somewhere around 70 something degrees, 73, 74, whatever, something degrees like that, then about 2 hours when you come back, that concentration of hydrogen gas within the water is going to be at 0.8 ppm. So hydrogen dissipates rapidly from water, and equilibrates with the air really quickly. So when you talk about portable hydrogen water bottles, there's actually been some tests done on this, by a colleague of mine, and actually shown that basically hydrogen water bottles half-life is about 110 to 120 minutes. It's a little close to 2 hours. Is not exactly, but some of these bottles are we're getting higher concentrations, so it's going to actually be a little faster probably than this. Maybe 1.5 hours, so maybe something around those lines, depending on the water temperature. But anyway, this is something that's important to understand, is that when you start to get to higher concentrations, you're actually going to have a shorter half-life. And this is due to the fact of, when you pressurize something to a higher PSI, it's going to cause the gas to equilibrate or rush out of the solution quicker. So an easy way to think about this would be like a champagne bottle. You have a champagne bottle and you pop it, carbon dioxide is just rushing out, because that champagne bottle has been sitting under 60, 70, 80 psi. And now you just released it, and now all that carbon dioxide is going to run out. And this is similar to what happens in hydrogen water. The higher concentration, the faster hydrogen gas is going to dissipate out of the water. So this means you need to be able to drink it quickly. And so I've actually experienced this myself. I've tested hydrogen water concentrations as high as 13, almost 14 milligrams per liter ppm, which is insanely high levels. But you can actually see this with these concentrations, that the water effervesces like champagne. Like champagne, we watch champagne, it look like magical bubbles just appear out of nowhere. You're looking at your champagne bottle, and you just see bubbles coming out, and you're like, where's the bubbles coming from? But they're coming out of solution. They're coming out of the water, and they're coalescing together, the bubbles, and then coming out of solution. And so it just looks like they just abracadabra Houdini out of thin air, out of the water. And hydrogen water does the same thing. You get the concentration high enough, it effervesces like champagne. It's pretty cool to see it. Okay, so dissipation and equilibration. It's important to keep in mind that H2 is fragile when dissolved in the water, and agitation will increase its rate of dissipation. And so I already kind of explained this point. You want to be careful about how you go about storing your hydrogen-rich water, how you go about drinking it, or even moving it around sometimes, because you can cause it to leave quicker. It's best to drink hydrogen water fresh right after you get done making it. Okay, so dissolved H2 versus undissolved H2. So this is a really important conversation because um, what's happening is that hydrogen gas, just like any other solute um, or soluble gas, can actually be dissolved into water. And what it means about being dissolved into water is that it's going to exist in a particular size of a bubble, which is called nanobubbles. So these bubbles range from anywhere between 1 to 1,000 nanometers, and they're invisible to the naked eye, so you can't see them. This is why I was just saying about with carbon dioxide that it's just abracadabra Houdini out of the water. Because you don't see the nanobubbles that are end up coalescing and undergoing this process of bouncing through water molecules called Brownian's motion, basically, and coming out of solution. And so this is basically what's going on with hydrogen-rich water. Hydrogen-rich water, you're dissolving that gas into water, hydrogen gas into water at a particular concentration that can gonna give or induce therapeutic benefits to your body. But in order for that gas to reach the parts of your body that it needs to induce therapeutic effects to, it needs to be dissolved into a nanobubble form. And so theoretically, if you want to have the most pristine hydrogen water on the planet, it would look like ordinary water because all the bubbles there would be no bubbles. Like all the gas would be dissolved. It would look like normal water. You would not even know you were drinking hydrogen rich water because hydrogen is an odorless, tasteless, colorless, non-toxic gas. So you wouldn't even know. Um, there is no such thing so far as the most pristine hydrogen water that you get no bubbles. Most times when you drink hydrogen-rich water, you will see visible bubbles of hydrogen coming out of solution. But the most important part is you cannot see nanobubbles with the naked eye. And hydrogen gas needs to be dissolved for you to get the benefits. If it's undissolved, you're actually going to see the bubbles and you're not getting benefits from those because they're basically already out of solution. They're going to be rising to the surface, they're going to be stuck to the side of the glass. When you drink, water's going to come off and then the bubbles are going to go into the atmosphere. Okay, so most times this dissolved hydrogen gas ranges from about 500 to 1,000 nanometers. And so I have a little study here, little source here talking about 600 nanometers of dissolved hydrogen gas from electrolysis. Electrolysis basically is decomposing water molecules into its natural element, oxygen and hydrogen. And so this is what these hydrogen water bottles are doing. They're performing water electrolysis, a particular type of water electrolysis that is going to produce pure hydrogen gas. And when they actually get dissolved into water, it's going to exist in the form of a nanobubble. So the actual smallest nanobubble probably that can be achieved is probably around 4 to 8 H2 molecules that are um, stuck together, and that's probably going to be somewhere around 1 to 2 nanometers in size, which is exceptionally small. Exceptionally small. I don't even know how to explain it to you how small that is, but it's very, very, very tiny. And most hydrogen water bottles or any hydrogen water products will not produce these type of bubbles. They're just really incredibly small. So I guess it's time to clear up some confusion. There has been talks, and this has been a while now. This is probably a couple years ago that they were talking about this, about basically molecular hydrogen is smaller than nano bubbles of hydrogen, which doesn't make any kind of sense. Molecular hydrogen is hydrogen gas, which exists in the form of a bubble when you put it in water, just like any other bubbles, just like the bubble you see on this little photo. So anyway, so I'll just read what I have here. These nanobubbles are not smaller than molecular hydrogen, which is approximately 0.1 to 0.2 nanometers in size. So a hydrogen molecule is about 0.15 nanometers in size. To put this into perspective, this is approximately about 10 to 15 times smaller than DNA. Like the width of the double helix of DNA is about 2.53 to 3 nanometers. So this is really small. High molecular hydrogen is really small. It is the smallest and lightest gas in the universe. It's the smallest molecule in the universe. It's really hard to fathom. And this is why I actually have come up with a video called How Small is H2. You guys should check it out if you're the first time watching any of these videos. Because I actually I don't make you, but you could if you want to, do a experiment where you take a strand of hair, you look at it within vertically at the light to look at the width of a strand of hair, and you can fit approximately 3 million hydrogen molecules across the width of a single strand of hair. So it's mind-boggling small. And so some of the smallest nanobubbles that exist in these products are probably around 20 to 200 nanometers, which is about 500 to 2,000 times larger than the hydrogen molecule. So if you hear anyone talking about molecular hydrogen is smaller than nanobubbles of hydrogen, then they are either severely confused or ignorant of the subject, or I wouldn't listen to them. I'm not going to say that they're trying to get over on you, but they could be trying to get over on you. It's just that doesn't make any logical sense once you actually know what you're talking about. Like I say here, there is nothing smaller than hydrogen or hydrogen gas. Hydrogen is the smallest atom. It is the first on the periodic table. It is 1 proton, 1 electron. Molecular hydrogen is 2 protons, 2 electrons. It is incredibly tiny. All right, measuring molecular hydrogen in water. So the concentration of H2 dissolved into water is expressed in ppms, ppb, or milligrams per liter. ppm stands for parts per million. ppb stands for parts per billion, and milligrams per liter stands for milligrams per liter. So how are they related? Well, 1 ppm is equal to 1,000 ppb, and ppb is obtained by multiplying the ppm by 1,000. So that's pretty much what it is. And ppm is equal to milligrams per liter. Okay, so I'm explaining really quickly why you will hear me say this all the time, where I say ppm or milligrams per liter, and I'll do them. I will in exchange. I will. What's the right word here? I would. I readily exchange the two when I'm talking about hydrogen-rich water, or I'll even say milligrams per liter or ppm. The reason for this is most people are more common. Most people are the majority of individuals searching for hydrogen-rich water, and these companies are going to use ppm, and so it's more commonly known. But milligrams per liter is actually a better unit for us to use for us to understand hydrogen-rich water, and they are basically identical. And so I'm gonna read this here. ppm in the context of hydrogen water means that there is 1 part of hydrogen in a million parts of water. 1 liter of water weighs million. Sorry, 1 liter of water weighs 1,000,000 milligrams. Having 1 milligram in 1,000,000 milligrams is equivalent to 1 part in 1,000,000. So, based on this understanding, ppm and milligram per liter are the same. They're just different ways of expressing the same unit. So why is milligram per liter better than ppm or ppb? Well, when you actually use milligram per liter, you can precisely track the amount of H2 that you're ingesting per day in milligrams. So this is what you'll see anytime you take a medicine or anything like that: 500 milligrams of acetaminophen or 500 milligrams of ibuprofen or blah blah. They're always going to be talking about it in mass or in milligrams. And so when you're doing this, you can actually calculate how much hydrogen gas you're ingesting per day, because in the research it suggested that 1 to 3 milligrams per day or more of H2 is recommended to obtain the therapeutic benefits of hydrogen gas for the human body. So when they look at the hydrogen studies as a whole of human data, they're administering between 1 to 3 milligrams of H2 per day or more. Some studies are up to like 15 milligrams a day of H2 via water. And they're seeing statistical improvements in a host of different disease models when it comes to hydrogen water studies. And in order for you to know how many milligrams you're drinking, it's probably better to use milligrams per liter than you would do ppm. and it'll help you kind of determine the health benefits, because hydrogen also seems to be quite dose dependent, meaning there's a minimum amount that you need, and if you get a greater dose, you get a greater effect. So in other words, if you can get 3 milligrams of H2 per day instead of 1 milligram of H2 per day, then that's going to be more efficacious towards deriving benefits for hydrogen acting on your body than it would be otherwise, right? This is just kind of where the study is, right? This is where the research is right now. So let's go through some do's and don'ts about measuring hydrogen in water. So first and foremost, the only valid way of measuring hydrogen gas into water right now is either very, very expensive devices, such as gas chromatography, the Unisense microsensor, things like this, or H2 Blue. H2 Blue is a test reagent that has had verifiable results and been compared to has been compared to gas chromatography for its accuracy. And H2 Blue is dependable and reliable if you use the correct technique and you actually kind of learn how to do it. I have a video about testing hydrogen water bottles and what you should expect when you're testing with H2 Blue at home versus some of these laboratory instruments, or even just me using H2 Blue. I've been using H2 Blue now for over almost a decade. And so H2 Blue is somewhat of an art. It's rather than a science. You have to kind of figure it out how to do it really well. And secondly, I go through a host of methodology of how I'm testing these products that just not being done with everyday consumers at home. So, but with that being in mind, this is the most convenient, easy, and reliable tool for measuring and detecting hydrogen gas dissolved into water. Do not use any other reagents. Do not go to Amazon or any of these things and just look up hydrogen test reagents. My company already tested several of these reagents, and I would say nearly every single one we've tested has been inaccurate, grossly inaccurate. So they basically inflate the results, or in other words, they dilute the reagent, which is colloidal platinum and methylene blue, and so they probably dilute it so that the readings are higher. They look higher. So 1 ppm will look like 3 or 2 or something like that. And it can give you a false sense of confidence. So don't use this. If you want to see the report, we can link it in the description as well for you guys to not actually look at that. Not go in that direction. If you want to buy H2 Blue, you can also look into the description and you'll see a link for our recommendation of H2 Blue. You can go there and you can find it. Okay, so let's go through the do's. So what you want to do is you want to make sure you obtain fresh water for your beaker, and it's best to fill it at a 45-degree angle. So I actually have a beaker right here. I have so many beakers, but anyway, it's best to fill it at a 45-degree angle to let hydrogen water slide down the beaker and not splash. And so actually I have a whole video for this too, but and then you want to make sure that when you're using H2 Blue, you fill the water up to 6 milliliters, where the meniscus, you see my image over here, the meniscus of the water is slightly above the 6 milliliter line, and the surface of the water is going to look about around 7 milliliters. If you don't do this and you don't do it rightly, you can skew your results by 25 to 30%. And so you also want to hold H2 Blue within the beaker itself. So it's best to do this technique. You do this. Then if you were to do this, drip, 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 drip. The closer you can get this beaker, I'm gonna drip a drop down. Closer you can get this beaker down to the water, the better, the less splash, the less agitation you will have. Which means you're gonna have better results. I also talk about doing the single drop method or the loaded drop method. You can watch my video to learn about that. I'll talk about it here in a little bit. Okay, so when you're actually testing for it, each drop of H2 Blue counts as 0.1 milligrams per liter. So you can simply just count the drops. If a drop clears, so H2 blue will turn clear if hydrogen is present. If hydrogen gas is not present in the water, it will stay blue. If it turns clear, then you know hydrogen gas is present. You can continue to add drops, and you can count the drops. If you count up to 10 drops, then you know you got 1 ppm. You count up to 20 drops, you know you got 2 ppm. Count up to 30 drops, you know you got 3 ppm. That's how that works. Once the water remains blue, you've reached a titration endpoint, and you reach the titration endpoint, and you can actually know what the concentration of hydrogen gas is in the water. So let's go through some don'ts. Okay, so you do not want to take your time getting your sample. H2 begins to leave the water immediately. So once you crack the seal on your hydrogen water bottle or something like that, hydrogen gas is going to start to leave immediately. So you want to move swiftly. You want to make sure I have all your materials laid out and ready to go for your test. And then you do not want to pour the water 90-degree angle, like I was saying. You don't want to take your water here. Let's use this, and you just pour it like this. You don't want to do that. You want to do a 45-degree angle. And then you do not want to stir the water vigorously. So you do not want to. H2 blue comes with. Let me see here. H2 blue comes with one of these things. They come with a stir. I don't use the stir because it can agitate the water too much and make you lose hydrogen. But if you use the stir and you're stirring like this, you're going to stir out a good portion of the water, a good portion of the hydrogen gas, and therefore your results are going to come back low. You want to be very gentle in your stirring to clear H2 blue and get it to react with the hydrogen. Or you can do my technique, but it takes a lot of practice, which is a small swivel. It's a little swivel. And that's a little harder. So you take a lot of time to learn how to do the swivel trick, but like you can actually watch it in my video. You also do not want to shake the beaker vigorously. You do not want to go crazy or anything like that. And then you do not want to move the beaker. You don't want to do it in your hand. Your hands move and stuff. It's better to set the beaker down on a solid surface, and then bring H2 blue to the beaker and keep it stationary. These are tips for ensuring you get accurate results. I talk about this in both of my videos about measuring molecular hydrogen in water. I have a part 1 and a part 2, and we kind of go over this stuff to kind of break these things down. And then lastly, I think you should go watch our videos. I talk about all the stuff and more in depth in my H2 minute videos. You should also go take your MHI courses. And so MHI is Molecular Hydrogen Institute. If you don't know what that organization is, they're a science-based nonprofit, 501c3 nonprofit for molecular hydrogen therapy, and really, I should say, molecular hydrogen research, and for funding research or pushing research or bringing awareness to research. There's courses that are fantastic to help you understand the basics of molecular hydrogen, basics of kind of hydrogen chemistry, and just understanding hydrogen therapy as a whole from a scientific standpoint. And in fact, I don't know if you all know this, but they actually have a way that individuals can basically subscribe and get different tools and things like that, resources from MHI, and I think you definitely should want to go ahead and investigate that. MHI is a great organization, #1 authority for hydrogen research online, and I'm actually the chairman and committee leader for the educational branch for MHI too. So I think it goes hand in hand. That you guys should go check that out. I think lastly, just continue learning, man. Continue learning. Continue watching H2 Minutes. We're gonna be putting out more content, and I think this is just the beginning of hydrogen water. You guys are gonna see a lot more of it. Like I said, I've been in this industry now for over a decade, and so I've seen the ebb and flow, but anyway, it does seem like this time is a little different. So we actually might see the rise of hydrogen to become mainstream, and you guys will actually see truly how amazing this wonderful little molecule is that can be dissolved into water. You can have the 1-2 punch. You can get hydration and hydrogen all at the same time. Alrighty, that's my presentation. Please like and subscribe. Hit the notification bell if you like this presentation. If it covers some details to help you kind of understand that there's far more science to hydrogen-rich water than just some companies wanting to sell you a product. You have to separate the two between marketing and companies versus what is actually real, and based on the physical chemistry of hydrogen-rich water and what's going on with that and what's happening in the research. And that's what my channel does. That's what my company does, is kind of help bridge these two gaps. The company bridge these two gaps, the research and the market. So I'm smack dab in the middle. I'm here to help everybody. So I hope you enjoy this video. I have another presentation probably coming out you guys here pretty soon as well, because this is what I be doing. So anyway, I hope you guys enjoyed it. See you later. Deuces.